If you recall, this week has been about using alternate descriptions of R2 and R3. The style of description that we're doing is replacing one of our distance coordinates with an angle coordinate. We started going from rectangular coordinates or Cartesian coordinates in X, Y to polar coordinates in R and theta, where we replaced, instead of having two distance coordinates, we have one distance coordinate and one angle coordinate. What that required was that we have an extra factor turning our angle into a distance so that we could calculate area. The same thing happens in a triple integral, where we convert one or two of our coordinates to angles. So we either have three distance with rectangular coordinates, we have two distance and one angle with cylindrical coordinates, or one distance and two angles with spherical coordinates. So the big idea here is that we're just using angles in increasing amounts to describe locations in three-dimensional space. The same thing applies. We are describing our three-dimensional space using one or two coordinates that are angles, not distances. This means that when we go to set up triple integrals, that dv factor, we're multiplying the value of the function by and keeping that constant on some small chunk of the solid over which we are integrating. Some small chunk of dv needs to be a volume. For rectangular coordinates, no problem. X, y, and z are all distances, so dx, dy, and dz makes a volume. Nothing to worry about here. This is the normal. No, this is not the normal. This is the one that we're most familiar with. Yes. I'm recording. So for dv, we can write dv as dx. In rectangular coordinates, dx, that's a distance. dy, that's a distance. dz, that's a distance. So this is going to be a volume. X, y, and z are all distances. I've got cubic distance, which is otherwise known as volume. In cylindrical coordinates, cylindrical coordinates, the coordinates are all familiar to us. Rectangular coordinates and cylindrical coordinates are very closely related because they just take the two that we're familiar with, Cartesian coordinates and polar coordinates, and add a z component, add a z coordinate, add some height. So here we have a theta is measured from the positive x-axis, showing our favoritism for x and y, and r is the distance from the origin. What we did with polar coordinates is we took our angle d theta and we looked at how far we were from the origin, just using arc length of r times theta. So we need to turn our angle into a distance so that when we use it in the volume, it becomes a volume. And the factor that we include is we just multiply by the distance from the origin. So our dv in cylindrical coordinates, dr is a distance, and dz is a distance, but d theta is not a distance. So now we're not, if we just multiply d theta times dr times dz, we don't get distance. We just have square meters or square feet if we want to be old school. But if we look at where we are in the solid W, we can turn d theta into a length by multiplying by that distance. In cylindrical coordinates, we do the same thing. To turn d theta into a length, we multiply by r. So dv in cylindrical coordinates is r d theta dr dz. The d theta, dr, dz can come in any order that we want. That's just determining in what order we integrate. But I want to write the r next to the d theta because that makes d theta into a length. That was the point. When we go to integrate, we integrate r along with our function. But when we set up dv, that r has to be there because it turns d theta into a length. Just like in polar coordinates, r turns d theta into length. Once with r d theta as one a distance multiplied by dr, a distance multiplied by dz, a distance. Now I have a volume. Now I keep using dv as a volume because that's the most visual thing that we can do, but it doesn't matter if these are actually all what the units of r, theta, and z are. Or it doesn't matter what our units actually are for distance in this scenario. The problem is that theta, and I keep talking about turning an angle into a length. The problem is that when we measure an angle in radians, we don't actually have any units. That's considered unitless. And so we have to install the units. And the units will be based on r. It's just the easiest one to think of is volume, so that's what we're running. For spherical coordinates, dv has one distance. So d rho, that's a distance. But d theta is an angle, and d phi is also an angle. We have one distance and two angles. So I need additional factors to turn theta and phi into angles. I just realized I didn't want to write these all together. Well, this is fine. I'll just use different locations. So d theta is not a distance. And d phi is also not distance. We're going to turn d theta and d phi into a distance in the same way that we did in cylindrical and polar coordinates. That's super repetitive because cylindrical coordinates are just polar coordinates with height. That's called double dipping. Another example of this is in the movie 23 with Jim Carrey. And he complains that the problem is he's going crazy because he's seeing 23 everywhere. Trust me, if you look for a number everywhere in your life, you'll find it. And you'll ignore all the places that it's not happening. So don't worry, the numbers are not out to get you. What was I talking about? Oh yeah, so he's panicking about seeing the number 23, and at one point he's ranting, and he says that the Earth is tilted at an angle of 23 degrees, and that the Tropic of Capricorn is at 23 degrees, and that the Tropic of Cancer is at 23 degrees. It's like, oh motherfucker, you're triple dipping here. The tropics are where they are because of the angle, the tilt of the Earth. That's all the same 23. That doesn't count as 3. So we got to Gimli this one and be like, oh, that still only counts as 1. Now you can go back to being crazy. Because at one point he starts adding up numbers in a date. And sometimes when you're adding up numbers in a date, you just ignore the century. But sometimes it doesn't work if you ignore the century. Like if you have a 1-9, if something happened in the 1900s, then you're like, oh, whoa. I can't have this extra 10 running around. So you ignore it. But if you're off by 2, then you're definitely going to include the century. It's like, oh, yeah, but it's 2023. So when we add them up, it's 3, 4, 5. It's 7, right? That makes sense. That makes a 7, right? But if you're like, oh, but this happened in 1961, then you're like, oh, the 61, 6 and 1 is 7. And they're like, oh, well, what happened to the 19? You're adding up the digits in a date. Why do you ignore the 19 when it's 61, but you include the 20 when it's 2023? It's because the 19 doesn't fit the pattern unless you make it fit the pattern, which means that you're cheating. Do you know what I mean? Don't be afraid of numbers is I guess the point. What are we talking about? Oh, yes. So theta and phi, d theta and d phi, not distances, and we're trying to make a volume, we need to make the distances. We are going to do the same thing. We're going to multiply by how far from the pole that point is. So here's a point. Here's a point at rho, theta, and phi. So rho is going to be this distance from the origin to the point. This is the only distance that we have. So this is rho. Theta is the same theta that we were using in cylindrical coordinates. It's the same theta that we were using in polar coordinates. But phi is the angle measured from the positive z-axis. We always have to pick an axis and measure the angle from that axis. In this case, we kind of need our x, y, and z, but here is our angle phi. So we look at where the point is, and we can see that that point is rho units from the origin. So to turn d phi into a length, we just need to multiply by rho. Sorry, yes, rho. So to turn d phi into a length, the point is the point that we care about that makes the angle here, where rho is. Sorry, where phi is. That's rho units away from the origin, so that's how d phi becomes a distance. To make d phi a distance, we just multiply by rho. The way we turn d theta into distance is multiply by r, but there is no r in this coordinate system. So previously, we had turned d theta into distance by multiplying by r, but there is no r. In polar and cylindrical coordinates, we multiply by r to make d theta a distance. But in this coordinate system, there is no r. I get rho, theta, and phi. But in spherical coordinates, there is no r. So we're going to write r in terms of coordinates that we do have. We need to write r in terms of coordinates that we have. I don't know why I'm having to color code all these. I have to now, though. I started it, so now I have to keep doing it. Coordinates that we have are rho, theta, and phi. Here is the thinking behind where these things come from. The TLDR is going to show up in a minute. I had an idea for a collaborative classroom where instead of just everybody at the same time shows up and does problems, I only allow half the class to show up at one time, not run the Zoom, and that half the class has to explain what happened to the other half of the class. And then just reverse the roles. Then the next day, the second half of the class shows up. First class, half the class is banned, and the second half has to show up to the first class. And then when you have a test, the score that you get on the test is the sum of the score that you personally got on the test plus the lowest score in the class of the people that participated in the test. So if like someone didn't show up, you're like, oh, we only got a half point. Make this a more, we're all in this together approach. Anyway, what are we talking about? Here's the thinking behind it. This is not what we have to remember moving forward when we're working for NASA and, I don't know, calculating triple integrals in spherical coordinates. This is the thinking. This is the problem solving that we are doing. We are looking at, we want to make dV a little chunk of volume because we're going to multiply it by the density. The function is going to be the density at any given point. d rho, d theta, and d phi is only part of dV, a volume. It doesn't make a volume because d rho and d theta are not, I'm sorry, d phi and d theta are not distances. So we're not getting volume. We turn an angle into volume by saying, how far are we from where the angle is? Look at that corner of the angle. How far are we from that? So to turn d phi into an angle, we say we are rho units away from where the angle happens. For cylindrical and polar coordinates, we were r units away from where the angle happens. We're not using phi and just multiplying by this distance because that's not where the angle happens. That's the one for phi. Theta is down here on the xy plane. So with the r that I've labeled down here that we were using before, totally, I would just multiply by that distance because that's the distance from the origin where the angle is happening down here in the xy plane. Does everybody see that? Do you see? Every time I say do you see, I think of that movie Red Dragon. It's called, do you see? No one's seen that movie, so. I also make reference to like The Matrix, and that movie is like 5 years older than almost everybody in the room. So that would be like if I was in college making reference to the movie The Sound of Music. What are we talking about? Oh, yes. So we need to write r in terms of coordinates that we do have, because we need the distance from the origin in the plane. That distance has to be in the plane where the angle is happening. That angle is happening in the xy plane. Rho is not that distance. So we're going to write r in terms of coordinates that we have, rho, theta, and phi. The way we're going to do that is we're not going to write r down here, but we're going to see this green page that's been turned from the xz plane through theta units. And notice that this distance r is also this distance from the z-axis to the point parallel to the xy plane. Now I'm going to take, now I've formed a right triangle. That involves rho with a hypotenuse of rho, an angle of phi, and the side opposite that phi is r. So if we just grab this triangle up here, I've got a side opposite of r. My vertical leg is the z-axis. Here is the point that we're concerned with, rho, theta, phi. Here is the origin down here, and so I keep saying that the translation, the transcription on this is going to be terrible because I might call here, there, there. The hypotenuse of that triangle is rho, and the angle phi is the angle between the hypotenuse rho and this z-axis. So we see that r is the side opposite angle phi, and the hypotenuse is rho. This is how we're going to write r in terms of rho and phi. So now r is going to be equal to rho times the sine of phi. We turn d theta into a distance by multiplying by r, but we don't have r as a coordinate anymore. That doesn't mean anything. I need to write r in terms of coordinates that we do have in spherical coordinates. That's rho, theta, and phi. And we can see that we can write r in terms of rho and phi with this right triangle. So r is rho times the sine of phi. So d theta becomes a distance when we multiply by r, but in spherical coordinates, there is no r. So I replace the r with coordinates that I do have, which is rho and sine of phi. Rho times sine of phi. So we did multiply by r, but I had to translate r into spherical coordinates. We turn an angle into a distance by multiplying by the distance from the origin in the plane, the distance in the plane where the angle happens. Question? It's fine. It's got Philip Seymour Hoffman in it, so it has good performances. Yeah, the thing that bugs me about sequels is when there's a movie that's clearly planned, they just plan on just having more movies. And it bothers me. And it's like, we're gonna make multiple movies out of this. And so instead of like organically happening, they just decide that they're gonna do more. Like I love Empire Strikes Back, but I mean it's really just not a complete movie. It's just not a whole movie. It's like it ends halfway in the middle of some stuff that's happening. So that in spherical coordinates, that's what we're going to need to turn our dV into a volume. So in spherical coordinates, our integral, a triple integral over W of some function of rho, theta, and phi, it's not good enough to just have d rho, d theta, and d phi. I also need rho sine phi times rho. I need rho squared. I'm going to write it out. We have d rho. That's a distance. D theta is going to be d rho or rho times the sine of phi times d theta. That's like the second factor in our volume. And then the third factor in our volume is rho times d phi. All this is our dV. Here's where we're multiplying them. Length, width, height. Of course, we simplify this so that our d rho, d theta, and d phi are all at the end. This is all just multiplication. So I pull a rho squared times the sine of phi. And so this is how we're going to write triple integrals in spherical coordinates. I got the two factors of rho. So rho gets squared. I need a sine of phi. And then I have the rest of the dV. D rho, d theta, d phi. That rho squared sine phi is what makes sure is part of the dV in our setup. Rho squared sine of phi is part of the dV in setup. When we go to integrate, it's part of the function that we integrate. So this part out here, this is still our dV. But when we go to integrate, we're integrating with this extra factor of rho squared sine phi. Just like before, if we make our function equal to 1, then our triple integral will just describe the volume of the solid W. So as before, if we let the function equal 1, just like if we make a single integral of the function 1, we get the length of the interval. If we make a double integral of the function 1, we get the area of the region. If we do a triple integral of the function 1, we get the volume of the solid W. Is everybody okay? Everybody looks shocked. Not in the room, just online. But that's because I replaced all your pictures on Zoom with a shocked face, the shocked face emoji. I'm just kidding. I didn't do that. Y'all get to control what picture shows up on Zoom. I admire your restraint. Let's look at an example of integrating a function 1 and including this extra rho squared sine of phi. Let's write a triple integral for the volume of a sphere with a radius of 5. So this is going to be our solid W. If we want the volume of the solid W, we just need to integrate the function 1. And in spherical coordinates, just like the name suggests, spherical coordinates, a bunch of intervals will give us a part of a sphere. Just like in rectangular coordinates, a bunch of intervals will give us a box. And in cylindrical coordinates, a bunch of intervals will give us a cylinder or a piece of a cylinder. Describing this super round object would be really inconvenient with square coordinates, with rectangular coordinates. So we're going to switch to spherical coordinates. We're going to make a triple integral of the function 1 because that will give us the volume of the solid. Now, in spherical coordinates, I can't just have d rho, d theta, and d phi. I need rho squared times sine phi as part of my dv. Then I can set up the rest of my dv, d rho, d theta, and d phi. Now I've set this up as a d rho, d theta, d phi integral. So my last integral is going to be my phi. My middle integral will be theta, and my first integral will be rho. We know we're not going to have to worry too much about this because this is a sphere. We're describing it in spherical coordinates. This is going to be a bunch of intervals. Phi needs to go from the top all the way down to the bottom. So phi will go from 0 up at the positive z-axis all the way down to the bottom where phi is equal to 2 pi. Sorry, phi is equal to pi. That covers the top semicircle and the bottom semicircle. Or sorry, top hemisphere and the bottom hemisphere. In the middle, I set up a theta, and I want to make sure I go all the way around. So I want to go from here where theta is equal to 0, all the way around back to here where theta is equal to 2 pi. So I'm going to integrate theta from 0 to 2 pi. That gives us all the way around the circle. And I want to go from the center of the circle all the way out to, the center of the sphere, all the way out to the edge of the sphere. So I want to go from the center of the sphere, where rho is equal to 0, all the way out to the outer surface of the sphere, where rho is equal to 5. The rho squared sine of phi is there to make dv into a volume. The way we've set this triple integral up, the first thing that we would do is integrate with respect to rho. So the first integral will be a 1/3 rho cubed. We should not be surprised by this at all, because we're trying to find a volume. Rho is distance. We should expect rho cubed to show up at some point, because everything else doesn't have units. Rho cubed sine of phi evaluated from 0 to 5. So 1/3, so 5 cubed is what, 125? Phi stays phi because we're plugging in rho, not phi. We haven't integrated phi yet. And when we plug in 0, we get 0. We still have to do the integral d theta, which is the integral from 0 to 2 pi. And we still have to do the integral d phi, where phi goes from 0 to pi. If we're thinking, gosh, the integration is going so easily, that's because we're trying to use spherical coordinates to find the volume of a sphere. So that's a good match. This would really suck if we were doing this in rectangular coordinates. But now we integrate d theta. The integral of 125/3 times the sine of phi is going to be 125. This is all constant with respect to theta. So 125/3 times theta times the sine of phi evaluated from 0 to 2 pi. That means we're going to plug in the 2 pi. So we'll get 250/3 times pi times the sine of phi. And then we're going to plug in 0 and we'll get 0. So I'm not going to worry about that. It is equal. That was the theta integral, but we still need to integrate again from 0 to pi d phi. Now we have all this constant, and we have to integrate sine of phi. The integral of sine is cosine, negative cosine. And then this gets evaluated from 0 to pi. I've dropped off the bottom. So here we are plugging in the endpoints. And finally, cosine of pi is -1, and cosine of 0 is 1. So cosine of 0 is equal to 1. Cosine of pi is equal to -1. That's going to change the sign here. And so I'll have 2 of these 250 over 3. So I'll have 500 over 3 times pi. If we notice that the 500 is 4 times 125, which is the cube of the 5, this exactly fits what we expect it to be. This is 4/3 times pi times the radius cubed. So it all checks out. We went super far over, so sorry about that. But here is the integration was remarkably simple because we were using the right coordinates. We were speaking the language of this solid, so worked out well. We do this in rectangular coordinates like I assigned for homework. I'm just kidding. If we do this in rectangular coordinates, it would be super messy involving trigonometric substitution. That's going to do it for today. That's going to do it for this week. I will see y'all on Monday. Everybody have a good weekend, and thanks for playing.